So this question was asked in GATE 2018 Electronics and Communication Engineering paper, in which you have given a Gaussian noise process N of t with two-sided power spectral density Sn of f, and this Gaussian noise process N of t is an input to a filter whose impulse response is given by 0.5 e to the power minus t square by 2, and you need to find out the power of y of t in watt. So the NPTEL reference for this question is Principle of Signal and System by Professor Aditya Jagannatham. The lecture is Fourier Transform Parseval's Relation. So the useful data for this question is, consider a system or a filter whose impulse response is given by h of t, and if the input of this filter is x of t, which is a random process, and you get output as y of t. So the relationship between the input and output PSD will be given by S of y of f equal to magnitude of h of f whole square into S of x of f, where this Sy of f is the PSD of output y of t, and this is the Fourier transform this h of f is the Fourier transform of h of t, that is impulse response of the filter, and this Sx of f is the PSD of input. So this is the first useful data for this question, and the second useful data is the Parseval's theorem. What is the Parseval's theorem? That is, energy in the signal x of t, that is minus infinity to infinity, x of t whole square dt is given by 1 by 2 pi times minus infinity to infinity x of omega square d of omega. So this is the second useful data for this question, and the third is that if you have given a Gaussian function, that is 1 by under root of 2 pi sigma square, where sigma square is the variance, and you are taking this integral e to the power minus t minus mu square upon sigma square 2 times sigma square dt, then you will get this integral value as 1. So this is the normalization of Gaussian integral. These three data are the useful for this question. So now in this question you have given h of t as 0.5 times e to the power minus t square by 2, and you have given the noise spectral density Sn of f as 0.5 watt per hertz, and this noise is input to this filter h of t, and you get output as y of t. So you can write the spectral density of output Sy of f, it is equal to magnitude of h of f square times s of n of f, or you can write Sy of f as is equal to 0.5 times h of f square. Now you need to find out the power in y of t. So there is one relation, that power in y of t will be given by area under the PSD. That is, if you integrate this PSD function from minus infinity to infinity, then this will give you the power in the random process y of t. So from this you can write power in the y of t is minus infinity to infinity Sy of f df, which is equal to minus infinity to infinity, this is 1 by 2 magnitude of h of f square d of f. Now, according to Parseval's relation, you can write this one as, that is integration from minus infinity to infinity h of f magnitude of h of f square d of f in time domain as, this is the energy in the h of t. So this is h of t whole square dt. So you can replace this h of f magnitude of h of f square df integration from minus infinity to infinity as minus infinity to infinity magnitude of h of t square. So now your power in the random process y of t becomes 1 by 2 integration from minus infinity to infinity magnitude of h of t square. Now, in the question you have given h of t as 1 by 2 into e to the power minus t square by 2. So when you put h of t in this py of expression, then you will get py of y is equal to 1 by 2 integration from minus infinity to infinity 1 by 2 e to the power minus t square by 2, and this magnitude square times dt. So you will get this one as 1 by 8 minus infinity to infinity e to the power minus t square dt. Now you need to find out the value of this integral. So from the useful data slide, you know that 1 by square root of 2 pi sigma square integration from minus infinity to infinity e to the power minus t minus mu square upon 2 sigma square dt is equal to 1. So in this integral, that is normalization of Gaussian function, you can put sigma square equal to 1 by 2 and mu equal to 0. So you will get 1 by under root of pi minus infinity to infinity e to the power minus t square dt as 1. So from this you can write minus infinity to infinity e to the power minus t square dt is equal to square root of pi. So you can put this value in this expression of py. So you will get p of y as square root of pi upon 8, which is equal to 0.22 watt. So the power in the random process y of t is 0.22 watt. So correct option for this question is option B.